Well, good afternoon. It's 2:34. We're 4 minutes late getting started in differential equations class, Math 238. And right now I'm the only one in the room, so I guess I'm going to get started with the recording, and then anyone who comes in will have to pick up anything he or she missed at the beginning. Now, where I have my mark, we're in Chapter 1, which of course is Introduction to Differential Equations, 1.2 Initial Value Problems, right at the bottom of page 17. Theorem 1.2.1, and we may have our first student here. Yes, we do. Good to see. I'm talking to myself, that's awfully bad company. So I'm glad you're here.
Good to know that even if no one's here, you still record for us.
What's that?
Good to know you still record for us, even if no one's here.
Yeah. Woo! What?
I was going to say glad to see everyone survived snowpocalypse, but
yes.
apparently not.
Maybe not. Yeah, they're still shoveling snow, I guess. I don't know. Or threw their backs out trying, you know. All right, I had just gotten started. We're at the bottom of page 17. If you do have a book, it's Theorem 1.2.1, Existence of a Unique Solution. And this is sort of one of those, they exist, but not how you find them problems. Okay? I believe I did.
What are those called from Cal 3 with and 2? The summation of whatever. Just so
right.
if it goes to 0 or not. Limits.
Yeah.
It's sort of like finding limits.
Yeah.
Yeah.
They don't have, they get them, but they tell you they exist.
Right,
exactly.
Right. You test if a limit exists.
So here's what I got in Theorem 1.2.1. If R is a rectangular region, oops, let me get my pen set up.
Page 17.
17, bottom of the page. R is a rectangular region in the XY plane, and we'll just make the XY plane here, going from A to B on X, and on the Y going from C to D. Okay, that's sort of the normal setup. Rectangular region on XY plane, so that A is X is between A and B, and Y is between C and D. That contains some point x0, y0. So this would be our x0, and this would be the point y0. Okay, so there's a point x0, y0. Okay? In its interior, not on the boundary, but in its interior. If f of xy and now, I said before, we're not doing partial differential equations, but we are using partial derivatives. So if f of xy and the partial of f with respect to y are continuous on R, this, by the way, is the region R, okay? So if both the function f of xy and the partial of f with respect to y are both continuous, not necessarily smooth, but at least continuous, on this region R, then there does exist some interval I0 around x0. So if you take your little h here, this would be a minus h, and this would be a plus h. Okay, some region around that x0, where h is greater than 0, some positive number, then this would be defining the interval I0, something around x0, okay? Contained in that closed interval A to B, every piece of that has to be within that. A unique function y of x, y as some function of x, does define on this interval minus h to plus, x minus h to x plus h that is a solution to the initial value problem. And this is going back to their rendition 2, which is the second equation back a couple pages earlier. Dy dx is equal to alpha of xy. Okay, this is the same alpha as we have here, and the partial of alpha with respect to y both have to be continuous. And that differential equation with the initial value of y of x0 equal y0. Okay. So basically, it just says it exists. Okay. So, going back. If you have some rectangular region R with some point x0, y0 in it, and here's what that x0, y0 is. There is a function y such that y at x0 is equal to y0. So this point right here is, you're going to ultimately be this point here. Okay. So if that point exists in this region R, then there is some, and you have this differential equation, dy dx equal alpha of xy. And this alpha of xy is continuous everywhere in the region. And the partial of alpha with respect to y is continuous everywhere in the region. Then there's some interval there that this function does exist, and with that boundary condition. And that the function does exist. It is the derivative. And to me, okay, it exists. We're assuming that it existed, or we wouldn't have even been talking about it. So I don't know. That one doesn't do a whole lot for me. Okay.
A test to confirm that there is a correlation.
Yeah. Their picture that kind of supposed to help describe this, I've drawn mine. Here is theirs. Okay. There's the A, B, and the CD, just like I did. I made the A, B a lot longer. There is some point in there, x0, y0, okay, in that region, on some interval I0, and the function there, the function exists and is continuous, it's partial with respect to y, exists and is continuous, and given a point that's there, then the function, it will solve that differential equation. I don't know. I guess there's some hidden meaning there that, we're supposed to be, ooh, why is that right? But
It's supposed to be like a graphic or something?
yeah, I haven't quite figured it out yet. But it's all true. I mean, that's all it's saying. There is a function that will work.
Not nearly as pretty of a proof as the Pythagorean theorems.
No, nothing. Yeah, you only have a few dozen or hundreds of those, I guess, by now. All right, so let's go in example 5, and we're going to revisit example 4, which I'm not really... Oh, I guess this is to show what we just did here, that it'll work for that. So let's go back to example 4. Let me erase this. We saw in example 4 that the differential equation dy dx is equal to xy to the 1/2. I think we've seen it a couple of times before. And partial of alpha with respect to y, I'm not sure we did this one. With that function, if we take the partial with respect to y, remember how to do your partials. With respect to y, you leave the x constant, so you just treat that like it's a coefficient. And derivative of y to the 1/2 would be 1/2. So I'll go this down here, y to the minus 1/2, which moves it downstairs too. So this will be the partial with respect to y. Okay. Now, this function of x and y, that's what this is, that's defined everywhere. no problem anywhere there. This partial with respect to y is not defined everywhere. Y first has to be positive and, of course, not 0, okay? So therefore, strictly positive, okay? But as long as you're anywhere where y is strictly positive, okay, and x could be anything, then this should have a solution, okay? This should have a solution. That's what the theorem tells us. And it says have two solutions whose graphs pass through 0, 0. Now that, no. The partial f with respect to x does not pass through 0, 0 because y can't be 0. Oh wait. That would be an indeterminate form. So I guess possibly it could. Okay. And that's what example 4 was supposed to have shown us. And if you look back to example 4, of course, the function y is equal to 0 is sort of like the trivial solution, and y is equal to 1/16 x to the 4th. We showed that was a solution. But that thing about the partial, we didn't use the partial in example 4. It doesn't seem to fit here. Hence, theorem 1.2.1 enables to conclude that through any point x0, y0, as long as the y0 is greater than 0 in the upper half plane, there is some interval centered on x0 on which the given differential equation has a unique solution. Thus, for example, even without solving it, we know that there exists some interval centered on, why not 2, okay? You didn't have to choose 2. You couldn't have chosen 0, okay? That wouldn't work. But 2, so x0 is equal to 2. And y is equal to 2. I mean, y at 2 would then have to be equal to 1. Now, why? Where do they get that the x0 would be 1? X is 1, y is 2. That would be f of xy would be square root of 2. And that would be 2 over 2. Okay. Now, seems like they pulled some things out of the air, which I'm sure what they're saying is true, but it's not particularly clear. Let's move on. Interval of existence, uniqueness. Suppose that y of x represents solution of the initial value problem that we had on the previous slide. The following three sets of real x-axis on the real x-axis may not be the same. The domain of the function f or y of x, the interval I over which the solution exists, is defined or exists, and the interval I0 of existence and uniqueness. Okay, I guess that's the difference. The I sub 0 says it exists and you have a unique solution there, not just any old solution. Okay, so anyway. I think we saw that, without rehashing it again, we saw that in example 2. We saw that, yeah, the solution exists in 3 different pieces, but to go through one point, you're fixed on which piece it is, because it has to be that that's where you had functions up here and one down here. This is the only place you had a negative y. Only place you could have a negative y. So the other 2 were completely out. So it seems like that's just rehashing that. I think I already made the assignments here, and I think somebody pointed out in the first section, but I think the ones since then are better. Not all of the odds were given in the back of the book.
Every second.
Okay, was it you pointing that out too?
No, what's his name?
Yeah, Jala, Muhammad Jala. I don't remember.
No, it wasn't him.
Okay, was it Justin? Dan. It may have been Dan. Yeah, I believe it was Dan. So, but I think in 1.2 they are there, but I'm not absolutely certain. Number 1, 3 or 5, 7 or 9, 11 or 13, 15, any of the odds 17 to 23, 25 or 27. I don't know that 29, 31, 33 would be there, but I do believe 35 to 37 would be there. And any of the odds 41 to 43 I think are there. But just do the ones that are back there. There are some discussion problems. Hardly ever are they there, but if you want to think through them, that's not a bad exercise to do. Okay. Now I'm trying to remember if, yeah. This next section, again, I don't really care for the organization of this book, but it seems to be the direction that most books take now. The first chapter is sort of a nebulous chapter saying, oh, look at this and look at that, without telling you how you got these things, but this works here and that works there. Sometimes this might, you know, why don't they just show you how to solve it? We'll get to that in chapter 2. I'm going to try to get there as quickly as possible. This is the last section here. And what this is basically doing is, you're using your name in vain. Okay, glad you're here. 1.3 is just basically showing you some of the models of real-life type problems that you use differential equations for. So without going into gory detail on these, let's just, hit these. Well, first, what is a mathematical model anyway? They can range from being fairly simple to incredibly complex. And some of the ones that come to mind, say in physics and other places, are actually partial differential equations, which really are complex, but we're not going there. We're just going to stay with fairly simple one. But a mathematical model would be taking a phenomenon and saying, how can this be explained or described using differential equations? Now, this is definitely not differential equations, but I just read a paper that one of my students turned in another class, and basically going from the, I don't know if either one of you have had complex variables, but on the complex plane, you have the real axis here and the imaginary axis vertical. Real axis horizontal, imaginary axis vertical. And when you're dealing with things, concepts on the complex plane, only time they're real numbers is on the horizontal axis, and those are all your real numbers there. Everything else is a complex number with imaginary parts to it. And when you're solving equations and doing things with it, there's sometimes you hit a point up there that is not defined or is hard to define anyway. You call that a singularity. And his paper was built on the premise that the Big Bang Theory, what started it was a singularity. It contained everything in an infinitely small point, and all matter, all energy, all everything was confined to a singularity, and then it exploded from there. Exploded is sort of a relative term. If you start with nothing, how can it explode?
It's always had the issue with the singularity theory, which is that, so you theorize that a black hole center is singularity, point of infinite density mass. But the singularity is by definition beneath the Schwarzschild radius, which theories make a black hole. So if you had all the matter and all the energy in the universe contained in a singularity, that would be inside of the Schwarzschild radius. It would definitionally have to be a black hole. How would it, if there's not an infinite amount of energy cannot escape a black hole?
Right.
So how would a singularity explode? It can't overcome its own gravity.
Right. And that is, and all the theories in the world that I've only read a couple of them, they just weasel their way around that and say, we don't know how. But it seemed to have happened. And when it happened, this is what the result was.
Like a point of infinite mass can't explode.
Right, exactly. So the word explode is probably not a good one. So we're not going to that deep a thing, but we are going to talk about mathematical models. Now, a couple of issues on it. Each mathematical models, and this may be exactly what we're talking about here, there is some specified level of resolution, okay, that you can talk about it within a certain framework, okay? And we make a set of reasonable assumptions or hypotheses about the system we're trying to describe. Sometimes these are too restrictive and they really don't work anywhere else. And one that comes to mind here, if you've done just a little bit of nuclear physics, which you may have gotten a little bit in your course, the Bohr model. It was a theory as a model, and it worked perfectly for hydrogen. But as soon as you tried to apply it to helium, which is number 2, it wouldn't work anymore. Just everything got way too complex for it. And then later they came up with models that did do a little bit better, but they were way more complicated. The Bohr model was easy to understand. Anything in quantum mechanics is easy to understand. Yeah, so, but it did. So, now, anytime your model has a rate of change, now sometimes that rate and most of the time the rate is a time rate of change, okay? That's a derivative with respect to time. Now, you could have other rates of change. I'm just going to give a real simple one. Most of you drove, I'm sure, to get here or something like that. You looked at your speedometer. That was the speed or velocity, change of displacement, the time rate of change of displacement, velocity. That's what it is. And when you accelerated this, the time rate of change of velocity was acceleration. Those are rates of change with time in the bottom. But as you were burning your fuel, you were doing so many miles, you traveled so many miles per gallon of gas. So there your rate was with how much gas you were using, not a time. So you had a rate of change somewhere in there. Most of the time it's a time rate of change, but sometimes it's not, okay? But anyway, that involves a derivative, okay? And then they have this little diagram about the, sort of going around in circles, your assumption, hypotheses, mathematical formulation, finding solutions, seeing if they work, going back and changing your hypotheses, that type of thing. So what we're going to do, that's all sort of the blah blah background here. Here are a few examples of mathematical models, differential equation models of various things. The first of these, don't know exactly which field you'd put it under. Generally, I think it goes under economics, but there's other places it could go. Population growth. Now, this could be,
bacteria, right?
yeah, it could be microbiology. It could be Yeah, anthropology. It could be insect. What is that? Entomology. Okay. And it could be, yeah, well, we'll get to nuclear a little bit later. So this is population dynamics, and it was first come out with an English, believe it or not, clergyman. But then if you think about it, sort of back in the really old times, sometimes the clergy was the most, and maybe sometimes the only educated person in a
kept records of the population.
Yes, and they would have, you know, as for his parish or whatever. Okay, but he was an economist, Thomas Malthus, and this is the Malthusian model, that the rate of population growth, the time rate of change of population, is proportional to the population. Okay, if you have a very small population, it generally can't grow very fast because of very few options for pairings, okay? Whereas a huge population can grow much faster because there's an enormously larger number of possible pairings of people to expand the population. Now, anytime you see a proportional sign, you can change that and add a constant to it. The rate of change of a population, time rate of change of population, will be k times the population, okay? The proportional sign changes to equal some constant k, okay? And that's in just about all of science in any way we're talking about it. So it's still used to model small populations over short intervals of time, bacteria growing in a petri dish or something like that. But that's a population model. Now the surprising thing is, somewhat surprising anyway, that just about a lot of the models that we're going to look at are going to look just like this. But they're not going to be talking about population, they're going to be talking about other things. But this is such a simple but very effective, usable type of a model. Radioactive decay, same type thing. The rate of, yeah, it's just k may be it will be a negative number. The ADT, where A is the amount of radioactive substance you have, is proportional to the amount of substance you have. Okay? So if you have a lot, it's going to decay more quickly. The rate of decay will be a larger number. And of course, then the ADT could be represented as some k times A. Okay? Now, in the first one, k is positive. In the second one, as I think this is what Peyton was saying, k would be negative. Okay? Because this is decay. As populations grow, radioactive material declines in its number because of radioactive decay. So that's the major difference there. A single differential equation can serve as a mathematical model for many different phenomena. Okay? They just threw this one in without a subtitle for it. The others were population dynamics and radioactive decay. They just threw another one in here. The SDT is equal to RS. Well, if you were a banker or something like this, is the growth of capital in simple interest, basically. The rate at which capital accrues is the interest rate times the amount of capital you have, okay? That's sort of a basic premise of banking, you know, type thing. All right. That didn't have sort of its own subtopic here. Now, for both of these, though, you have to have, at some value t, P of t, see, P is the dependent variable, T is the independent variable, So P depends on T, and at some specific value T, let's say P of 0, you would have some initial amount. At time T equals 0. If you didn't have any amount there, no population to begin with, you'll have no growth. Couldn't have any. Small population, then it'll be pretty small, the rate of growth, because like we said before, but then, larger population, but whatever. So you're always starting out with an initial condition. T equals 0 here. Now, it wouldn't have to be T equals 0, but that's usually the logical place to start, because usually that's what you know. You know at some fixed time what something is, let that be your 0 and count from there. There's no real reason for it to start at T equals 17, but it could. If you didn't start your problem until 17 minutes or 17 years after the initial setup, then you could start with it being something else. But quite often it's the initial condition, like how much of the radioactive material you had at the beginning. If that's going to be your T0, then that would be A0. Okay. All right. Let's go to a slightly different model, but it doesn't differ that much. Newton's law of cooling/warming, either one. This is the time rate of change of capital T usually stands for temperature, little t for time. Okay? And most of the time in physics, we want that capital T to be Kelvin, but not always. They didn't even have Kelvin when Newton came up with this, so you didn't have to have it in Kelvin. Whatever temperature scale you happen to be using, in fact, I think he used his own scale, okay? This was proportional to the variable temperature minus the, and I always have to check, they use sub M. I'm used to using A there for ambient. It doesn't matter. What this means, the time rate of change of something will cool will depend on its temperature, that's the T that is going to be changing, and then the T of the surroundings. So if you had a very hot object in this room, it's going to cool pretty quickly.
Isn't this the old first law of thermodynamics, T depth of the universe type equation?
Right.
Yeah.
Yeah.
The entire universe must be a fixed time old because it hasn't equalized temperature completely and will exist for a fixed time because all the energy is spread out across the entire universe evenly.
Yeah. Yeah, so it can be expanded to pretty large scale, but let's just take it in this way. If that object, so that one's going to cool really quickly. If it's an extremely hot object and the ambient is not that hot, then it's going to cool really quickly because that's a huge difference there. But if it's a very small difference, then it'll cool just ever so slightly, slowly.
Iron being red hot,
right?
Completely solid versus then being able to touch it.
Right.
So
exactly.
It would take a minute for it to be solidified. It would take an hour for it to cool down so you can touch it.
Right. So we this morning I ran a sink of hot water when I was cleaning up and doing things, and didn't let it go. And when I came back after I ate breakfast, it was still fairly warm because there wasn't that much difference between the room temperature and the sink of water. So you could still feel it was warmer than room temperature, but not by a lot. Several things were going on there. That's Newton's law of cooling or of heating, because it could be that your temperature here is less than your ambient temperature, so now it's got to warm up. It'll follow the same pattern. The only difference is it'll be a negative rate of change, because if it started, say, at 10 degrees Celsius and we're at 20, then that would be a negative on the right. It's going to be, the rate of change is going to be a negative, So, well, depending on what the K is. Well, just like we did before, dt, which just listening to it, that doesn't sound like it makes any sense. It's T capital T, D little t, would be some constant times T minus Tm. I keep wanting to put TA for ambient, but Tm. What do they call it? Surrounding medium. So that was the medium temperature, the air temperature. Okay? And again, and like I was just saying, this K is typically going to be a negative number. Okay? Because if you started off with a hot temperature here, a cool temperature here, this dt has to be negative because the temperature is falling. Whereas if it was started at cold, where the medium temperature, the surrounding temperature was warmer, then the temperature is rising, so the dt. That is a negative number, but this is a positive derivative. So that would give you, the K always has to be less than 0. Okay. There's one more. Here is one. The spread of a contagious disease. My wife's an epidemiologist in infectious diseases, so this is her ball of wax here. But I doubt if she went down to this level. She just uses statistics that use this level of a model. And that's that dx dt, where x is the number of people who have contracted the disease, is equal to K times X times Y. Whoa, where does the Y come in? Well, Y is the number of people who have not been, I think, let me make sure this is right. Yeah. Who have not been exposed to the disease or did not contracted the disease. Okay, so X is the number of people who, let's see, make sure I say it right, have been, number of people who have contracted the disease. Y is the number of people who have not. Okay? Now, if just a few people have contracted the disease, this is going to be a very slow-growing disease because not that many people have. But if not many people haven't been exposed to the disease, it'll again be very slow-growing because there's no one else to expose. Okay? If everybody has been exposed to it, then there's not that many left who haven't been. And actually, if you study this one, it gives you a curve that does something like this. Okay? It's called logistic curve, I believe is the name for it, where this would be your total population. So if your total population has been exposed, the rate is going to be going to 0. Okay? If not many people have been exposed, the rate is already close to 0. It's when you're somewhere in the middle there, you're going to have very high rates of contagion, you might say. And you studied this with a log curve, because that's a very difficult curve to deal with, because it has very steep slope in the middle, very shallow slopes at either end. So basically a log transform will really make that a lot easier to deal with. And it's called logistic regression. And that's where the logistic curve comes from. It's solved using a logarithmic transform. And Karen probably doesn't even think about log transforms, but she uses logistic regression all the time in her programming, letting the programming take care of the details of this, but that's exactly what you're dealing with. Okay. Now, I feel an urge to throw in a commercial announcement here. I just was hearing on the news this morning coming in. I think it was somewhere in the Pacific Northwest, but I may be wrong on that. They were having an enormous measles outbreak. And when they... Canada, around the Great Lakes area. Oh, maybe it's there. Maybe it's Midwest, not the Far West. I don't know. Somewhere they were, and where it started is an area that had very low vaccination rates. surprise, surprise, you know. And basically there's a movement out there, and I have yet to figure out what's the cause of it, but they're the anti-vaxxers, the people who just are against vaccinations because there may be some side effect we don't know about, you know, and so let's not do it. Well, those people are banking on the fact that most of the rest of the population will get the vaccination so that you're down here somewhere, okay? Very few people are going to be exposed. Well, actually, so you're up here. Most people have antigens, so they're hoping there's not going to be an outbreak. But if they get a big enough mass of people, you're down here somewhere. So if you do get, you got to go through this. Whereas to be vaccinated, you basically put all your population up here. Even though they've not had the disease, they have been exposed to the disease through the vaccine. And and the doctors are just beside themselves on it because the drugs have been, the vaccines have been studied and studied and studied and studied. And sure, there are maybe rare circumstances where people will have a negative response to it, but they're so incredibly rare. It's nothing like this, okay? And
some people don't understand what chemical compounds are. They don't understand, like, many vaccines contain mercury compounds. They think that exposure to mercury is toxic, period. But no, there are many mercury compounds that are not toxic, and that's what they're using. But it's not even metallic mercury that's really the problem. It's the organic compounds of mercury that are the problem. But people don't understand that either. I think a lot of people understand that chemical properties change very rapidly depending on the structure and everything. So,
and they all are grown in some medium.
Potassium in your banana is not going to cause you to explode. You know, something like that.
All these things are grown in some medium, and if you happen to be a rare individual who has a sensitivity to the medium, that could be what's causing the issue, but they usually pick things that are most people are not going to respond to.
Right.
So
different iterations.
Yeah, and it's called the adjuvant, is what she calls them. I'm not familiar with that term. But anyway, that's exactly what's happening to wherever that is they're having the outbreak. They got down because there were a bunch of a population somewhere that got down into this range, and then a small outbreak then rapidly expanded. And then sometimes even people who were vaccinated, you know, might get the disease if it's that prevalent, you know. So you just destroy it's just a mess. I have a niece who, her husband, really thinks if you keep your immune system up and stuff like this, you're going to be fine. And, you know, and his daughter is very healthy, so he doesn't see any reason to vaccinate her. But their son has asthma, you know. And so Karen keeps saying, okay, yeah, Polly may not have a problem with it, but if Polly does get it, she's not won't do her any harm. But then she'll bring it home and give it to Isaac, and then he'll have enormous problems with it because he's already, this wouldn't be measles, but he's a lot more sensitive because he has this other condition. And she said, it's not for Polly that you're getting him vaccinated, it's for Isaac, you know, so you don't want her bringing it home, even though she may not have I mean, when I was growing up, no one got vaccinated for measles. You just expected to have measles, you build up your own immunity and go. But you know, measles carries a lot of, you can have serious eye problems from it, you can have heart problems from it, you can have other things. And they found out the
grandmother is deaf permanently because of it.
Right.
From childhood,
Right. So they're just, the benefits way outweigh the problems. There are problems, rare problems, but the problems with the disease way more prevalent, you know, and could be in many cases, a lot more serious. So yeah, I'm sorry, shouldn't have got off into that. But there is another example of a differential equation. Now, this one in particular, because, like I said, X is the number that have been exposed, Y is the number that haven't been exposed, and for the life of me, I've never figured out why they need the extra 1 in there. But N, I think, is the number of the population. Yeah, a fixed population with N people. If one infected person is introduced, oh yeah, that's where it comes from, is equal to N plus 1. Okay, so X have been exposed, Y have not been exposed. N is the total population, but in order to get the ball rolling, you have to bring in one person who has been exposed. If this N is 0 and Y is equal to N, you never have a start. So you have to have one to bring it in. So then you could reduce this equation to X is equal to N plus 1 minus Y, and then this would be K times X times N plus 1 minus Y. I mean, sorry, I said it backwards. Sorry. Let's do it the other way. Y here and X here. Okay. Minus X. Okay. And now you have a linear differential equation with only X in it. Okay. And so you don't have two variables, you have just one. So then you can proceed from there. But it comes from that basic premise.
I'm sorry, is there a typo in the book? Number 5 is kx times n plus 1 minus x.
Yeah, that's what I have here. I started saying y, I changed it. Okay, let me go back and change this. I started saying x is a function of, yuck. Eraser won't come up. There we go. Okay. Okay. Yeah. Okay. That's what I meant to say. So instead of y, we put in n plus 1 minus x. Let me get my curve out of there. Okay. Okay. Yeah. That was my population up there. That was going right through the problem. Yeah, so it comes out the same. All right. Now, I know all of you loved your general chemistry, right? Okay. Here is an example of a situation. Let's see if I can remember what the names are. Not that it really matters. CH3 CCl plus NaOH. Sorry, I don't write very well. And they put the arrow one way. Later I'll explain that it can go either way. CH3 COH plus NaCl. Okay. So in other words, you start with, I'm not good on organic names. The first one is what they call T-butyl chloride and become a T-butyl alcohol. Yeah. Second?
It's butane and H3H4 is one thing, it's butane is H4.
Yeah, I think, yeah. So this, and I've got a 2 there. This is a 3. I don't know how I wrote a 2. Okay.
What is the other chemical after butyl chloride?
Say again?
The other chemical after butyl chloride, is that
it's COH.
That's
That's alcohol. OH is an alcohol.
Right. What about the other chemical after after.
That's
chloride.
sodium hydroxide.
Yes,
I forgot to put my A in place, so I wrote it out after. Sodium hydroxide.
Okay. Ooh, I expect this reaction to be a little bit violent. Sodium hydroxide and chloride.
Yeah, it's a very strong base, incredibly strong base, and it produces a salt, so you wind up with the alcohol in between. But
any reaction between sodium and chlorine, I would expect to be
yeah.
fairly violent.
And I like to picture these things. Here's the carbon with 4 bonds on it, and 3 of these bonds are methyl groups. Okay, CH3, CH3. But this one is a Cl here. And then you bring in an NaOH. Of course, that ionizes in solution, and the OH replaces the chlorine, and the chlorine replaces the OH, and that then gives you what is, okay, CH3, CH3, CH3. Now it's an OH here. That makes it an alcohol, T-butyl alcohol. And your result is sodium chloride, NaCl, which is a salt. Okay, so that's exactly what's going on here. Only the concentration of the T-butyl chloride, this first thing here, controls the rate of reaction. But in the reaction, 1 molecule of sodium hydroxide is consumed for every molecule of methyl chloride, thus forming 1 molecule of methyl alcohol. Okay, that's what this is. And 1 molecule of sodium chloride. So there's your reaction. So what we have here is the X denotes the amount of chemical. Why aren't they at all consistent here? I don't know. So basically what they're saying here, if I can substitute, let's suppose that 1 molecule of substance A, we'll let this be A, combines with 1 molecule of substance B, that will be the sodium hydroxide, to form 1 molecule of substance C. Okay. If X denotes the amount of chemical C formed in a time C, then A and B, goodness gracious, then if alpha and beta are in turn the amounts of the 2 chemical out, so this is alpha, this is beta, A and B, alpha, beta, that makes sense, doesn't it? As at the initial condition, time t equals 0, then the instantaneous amounts of A and B not converted are alpha minus X. If X denotes the amount of chemical C formed at time t, so that would be X is the variable amount. This was your initial, and this was initial, okay? But this is your variable amount of this one right here. Then without going into the chemistry of it, dx, the rate at which this is being lost or added, it depends on which, and rate being again time, derivative with respect to time, is equal to your proportionality constant, okay, times what you started with minus the rate at any time, okay, times beta, the rate of the amount, this one, minus X. So basically, you have a nonlinear in terms of X, because you wind up with the X squared over here. And because that is a second order equation, this is called a second order reaction. Now, they're not teaching us the chemistry here. In fact, they're doing a really lousy job of even explaining the chemistry here. But it's just showing you could have a differential equation in the amount of T-butyl chloride, whatever it happens to be, and it'll depend on how much you had of this originally, how much you had of that originally, and your rate of reaction will be a product of the two. Certainly, as less of this is happening, the difference there is growing. The difference here is the difference here is growing. The difference here is shrinking. Is that right? And that will all have an effect on how much is being produced. Again, they did a lousy job, I think, of describing the chemistry of it. It's just showing you samples of differential equations. This would be a nonlinear. And in fact, they call this a second order reaction because you have an x squared in there, not a linear reaction. Now, again, you don't need to know these things. It's just, these are just examples of applications of differential equations. Okay. Here's one. A lot of physics books love this one, or math books in general too. Okay, you have a big tank here with an inflow, a big source of water coming in, or whatever liquid it is. This happens to be brine. Okay, you have a certain amount in here to begin with, and you know that amount, and you're mixing it completely. So here's your mixer here, turning and mixing it. And then you have a smaller amount of brine coming out the bottom. Okay? Oh, no, they have the same amount. They just, their picture makes it look like it's very different. Okay? If this was just pure water to begin with, you'd have brine coming in at a certain concentration, salting up the water, so what's coming out would be salty, but not as salty as what was coming in. But at some point, it keeps approaching this, but it never actually gets there. It's a lot like that.
Yeah, it's a limit equation.
Yeah, a lot like your disease. You know, it'll approach the population, but it can't exceed it. So it will approach the amount coming in, but it'll never, of course, exceed it.
The brine is by definition saturated.
Right.
You poured into a substance that wasn't saturated, so no matter how much brine you add, you could never saturate.
Completely, because there was a certain amount there that wasn't. Yeah, right. Exactly. So you could write this differential equation, and they actually give an example of this one. I don't know why this one, but dA, that's the, let me see what A is, denotes the amount of salt in the tank. So this is salt in the tank, okay? dA dt would be equal to the input of salt minus the output of salt.
Essentially the opposite of diluting. I'm not sure what the name for it would be.
Yeah. Concentrating? I don't know. Okay. And they actually put some numbers in this one, and the concentration of the input is 2 pounds per gallon. Now that's a concentration. That is a rate, but it's not time rate. Okay? So, and if your input rate was 3 gallons per minute, okay, then that would be 6 pounds per minute would be your input of salt. What's that?
It's crazy to think that a gallon of water could dissolve 2 pounds of salt.
Yeah. And okay, the concentration of the salt in the outflow, the A of t is the amount of salt in there at any time t. And initially that could be 0 or it could be some other amount. And this was 100 gallons in the tank to begin with. Okay? So your output rate would be dA dt. Wait, I'm sorry. Let me clean that up a little bit. The amount of salt in the tank, this is the amount at any time t, so A of t, and I'm sorry I no, divided by 100 gallons, because that's the total in the tank at any time t, because the inflow is the same as the outflow. So you always got 100 gallons in there of whatever it is in there. So you have the rate of change of the salt content in the tank, the ADT, is equal to input, which was 6 pounds per minute. Okay, 6 pounds of salt per minute, minus the outflow rate was A of t over 100. Okay, times and it was going out at 3 gallons a minute. So, let's see. So you can rearrange this, and dA dt, and we will be doing this later, plus A of t over 100, or 100 times that, is equal to some constant 6. That's how we're going to set up a lot of our linear differential equations. The ADT, and then this could either be a constant or a function, either one there. This is just the coefficient of that. And we will be dealing with that later. We're not there yet, but this is one of the examples that you would be doing something like that. Okay. Now, what if you had no inflow and you were draining a tank? There's another problem, okay? And this is, well, let me start from scratch here, because this is a different problem, okay? This time we have a tank, and we have a little hole at the bottom that you're draining it through, okay? Torricelli's law states that the speed v of the efflux, the flow out of water through a sharp-edged hole at the bottom of a tank, filled to a depth h, so this would be your depth here of water, okay, would be, and this is Torricelli's law, V is equal to the square root of 2gh. Now, you might ask where he got that, and you can look that up if you want to, but anytime you see a velocity, that's the time rate of change of position, you might say. So that's the rate at which it's flowing, okay? G, of course, is acceleration due to gravity.
The rate Torricelli's equation.
What's that?
It's interesting that the rate isn't affected by the size of the hole. The flow rate is obviously velocity times the surface area, but it's amazing that the rate, the velocity itself, is not affected by the size of the hole.
It is affected by the height.
And
that
acceleration of gravity.
Yeah, and so if the height goes down, which it will, then the flow rate will go down because there's not as much pressure on it, because pressure is related to the height. Okay, so now little v is velocity, capital V is volume. So you get a differential equation here. This is capital V here, dt. The rate at which the volume is decreasing is equal to minus AH. And again, they're throwing in some terms here. The area of the hole. So that's what you were talking about. AH is the area of the hole. Okay? And so it does depend on that, times the square root. The velocity doesn't, but the flow rate does. Times 2gh, the square root of 2gh, which is your velocity. So the area times velocity will be your flow rate.
Typically, they keep choke the diameter not the opposite of the tank. The tank is constant velocity.
Right.
It depends on the
Yeah.
size.
Okay, so there's another differential equation. Okay, now they throw another twist into it, and this is negative because your flow rate is decreasing as the height is decreasing, and so your volume is decreasing as well. So it does have a negative. If you were talking just about height being your variable, not the volume of the tank, then the height is the area of the tank. The volume is the area times the height. If this is a regular tank, circular, right circular cylinder tank, then you could, if the area is constant, then this would be area of the tank, cross-sectional area of the tank. Do they use T? No, they use W. I don't know why W, okay, times dH dt, because the height is the only variable decreasing here, not the volume. The volume is only because of the height, and that would be equal to this. And then divide both sides by A sub W. And there you've got, you've got another differential equation that you could use. Forget about the volume. It all depends on the height. Okay. Have y'all all had your your physics 2? Okay. Remember Kirchhoff's laws and those kind, well, not Kirchhoff's laws. Did y'all get into RC circuits and LRC circuits? What's that?
What do they stand for again?
Okay, L is inductance, and C is capacitance.
Okay. Yeah,
Okay.
Inductance and capacitance.
What's that?
I know the basics of conductance and capacitance.
Yeah. Okay.
Or inductance and capacitance. Yeah.
And this is dealing with Kirchhoff's second law, where there you're supposed to be measuring voltage drops and rises, falls and drops, and usually we use just resistors in them. But you could also use inductors and capacitors in them. If you do that, you're no longer dealing with resistance alone, you're dealing with impedance, which resistance is a type of impedance, but so is inductance and so is capacitance. So if you're dealing with that,
Against the use of inductors as chokes.
what's that?
Against the use of inductors as chokes, like in the fluorescent light and stuff like that.
Right. And here are the basic rules that you use. If you had, this is going to be a new diagram here. These are just examples of differential equations, okay? If you have a E as a function of time. Now this is your EMF, electromotive force, or voltage, or whatever you want to call it. That's your power source, okay? And in the process of you're going through an inductor, that's your L. You're going through a resistor, that's your R, and you're going across a capacitor, and that's your C. So this is your resistor, and this is your capacitor, okay? And that's why this has to be as a function of time, because you see when you first close this circuit, the voltage is going to go, you're going to build up charge here, but then your current is going to decline. It's going to start at a max and then decline, because once it piles up all the charge here and deletes all the charge there, you get the fixed whatever the limit of that capacitor is, okay? Well, the rate at which the current is flowing, that's your inductor depends on the rate of current flow, and then your resistor just handles whatever is coming.
Right.
so to speak. Okay. So basically your current is changing in this, mostly because you're, and that makes your E have to change as well. So your inductor is L di dt, because like I said, depends on how much current is going through there, the rate at which you have current flow. Your resistor is just IR, okay? That is your current, the voltage drop across the resistance, I times R. Now, I is a variable current. That's why it's little I, okay? And then your capacitor is 1 over C times Q, how much charge is piled up on one side or the other. Well, then your variable here has to be your Q, not your I. But I is equal to dQ dt. So this will be R times dQ dt. Well, this will then be L times d2Q dt squared. Okay? And then this will just be Q. So what you have is a second order differential equation in charge, L d2Q dt squared plus R dQ dt plus 1 over C Q is equal to E as a function of T. Okay, there's your independent variable there. E is just dependent on that. Your Q, I'm sorry, yeah, T is independent. Q is the dependent variable depending on what time after you close the switch on this, and these other constants will determine what's going on there. Pretty complicated looking, but I mean that's Kirchhoff's second law says the impedance drop around there is equal to the voltage that you have here. Okay. Surprisingly, Newton has yet another.
It's time.
Oh, is it time? Yeah. How time flies when you're having fun, right? Thanks for telling me. I have my watch in front of me, but I wasn't paying attention. Yeah, you got it. Okay, we'll begin there. This is just sort of yakking here. We're almost through with this section, which is almost through with the chapter, which means I'll try to have your test ready next time. If you want to try a couple of problems with population dynamics, 1 and 3 would be good. I hope those answers are in the back. If they're not, just do the one that's in the back. Newton's law of cooling or warming would be number 5. Spread of disease or I don't like the way they say this. The spread of a disease or technology. I think what they mean, like a virus in a computer virus, how it can spread, is just like the spread of a disease.
I mean, it might be like the adoption rates of technology.
It could be that way too, and maybe that's what they mean. Yeah. But it just seems strange, equating or somehow equating diseases and technology together. That just sounded bizarre. Okay, that's number 7. Mixtures, they had 9 or 11. Draining a tank was 13. That's Torricelli's law. And by the way, Torricelli, Newton, any of these people would be potential paper topics since we're mentioning names. Kirchhoff could be one because he uses a differential equation.
Really?
Huh?
Kirchhoff, a lot of stuff.
Yeah. So series circuits, that's 15. We'll hold off there. Newton's, well, I don't know, falling bodies, where is that? Oh, okay, yeah. We'll pick up there. Newton has at least 3 in here. 4, maybe, 5, 6. He's all over the place here. Of course, father of modern physics. Okay, not modern physics. Good deal. We'll pick up and go the rest of those later. But it'll just give you a good idea of how differential equations can be used. And then next time we'll get into chapter 2, which is really, to me, the